All right, so we're back here. So let's finish up this example stuff here with the count occurrences example. And this time the set isn't going to work because basically this time we don't want to just count how many words appear or how many words of a specific type group. We want to know how many times does a specific word appear. Okay, so what we need to do then is we need to parse out this string. And so what we do is we create an array of each individual word. Okay, so we're basically splitting it based on, I think this splits on a punctuation too. But we're going to split it out into the different words, right? And then we're going to convert them all to lowercase. Okay, we're going to take all that text and do it to lowercase. This is not the only way you could have done this. You could have also taken this and taken the whole string of text and said, you know, text equals this thing dot to lowercase, right? You could have put over here text equals text dot to lowercase, right? And then you wouldn't have needed to do all of this here. You could have just gone, you could have just then done this here. Either way, you wouldn't have needed this for loop then. But anyway, point is, so basically we're saying, okay, now for each one, the key is going to be the words at a specific index. All right. So we're going to say, okay, so the first word, if the key length is greater than 0, so if it's more than one character, sorry, more than 0 characters, so it's not the empty string. All right, then we're going to do something. So let's skip on down. If the key is only 0 characters, so it's an empty string, we're not going to do anything. We're not going to add the empty string to our map. Okay, that's fine. Second thing we're going to test is now if the key is some piece of text, something that we want to track, we're going to say, okay, does the map contain the key? So if the map does not contain the key already, so we haven't found this word yet, okay, then we're going to put into our map the key and 1. Why 1? What does 1 mean? Right, since this is the first time we've found this word, it hasn't existed in our map yet. It doesn't exist in our map because we haven't found the word yet. Now we found it one time, right? So we're going to put in the value of 1. Otherwise, okay, this key exists in our map. This key already exists in our map. All right, so now we need to get the value that key points to. So maybe it's 1 still. The second time we find this word, it'll be a 1. The third time it'll be a 2, and so forth. We get that value, we add 1 to it, and then we put into the map at that key our new value. Right. Now, why couldn't we have just done this? Why couldn't we have just done this? There's a whole lot of things wrong with this right here. For starters, it would get a compiler error to start with. So if I were just to do this, let me show that it compiles first. So this compiles on its own first. If I were to do it like this, I would get a compiler error, right? the thing is that this plus plus requires a primitive type, right? And what this map returns is, as Eunice has stated here, is that it returns an object. And I can't just add one to the object. The other thing is I cannot just change the value of what's in the map just by doing this plus plus. I can't say map.getKey can't do this, right? Because this returns an object, but I can't set it. I can't set a method to be a value. I can't put a method on this side of an assignment statement. Okay? The way to change the value in a map is to put it into the map. So we put at the key the new value. Okay. Go ahead and get rid of that because I don't want you guys getting confused. All right. And then what I'll do is for each map is I'm going to say, what is my key value pair? All right, so if I run this, so notice here we have A, class, fun, good, have, morning, visit. Let's see. So good shows up, what, 3 times? Good, good, good. Have shows up 3 times. A shows up a couple of times. And everything else shows up 1 time. Now, what if I wanted to combine these two? Now, this is a thought thing. I'm not going to go over this one because we need to go ahead and get into the efficient algorithms slides. But what if we wanted to combine the keywords with the count occurrences? Consider what here, no matter what, my map values, I will never have a 0 as a map value. But what if I wanted to count the keywords in a file and I wanted to be able to have things like try. Try is one of my keywords. And I want to know that it shows up 0 times, because if you look at my test.java, try doesn't show up, does it? So I want to know that try shows up 0 times. So I want the map to say key try value 0. Key abstract value 0. Key package. All right. Key, where is it? Package value 1. Okay, so I want to have the map have all of the keys but zeros for the ones where they don't appear. Okay. Yep. All right. So it's something for you to think about. We're not going to go over it here, but you could imagine that it might be an interesting exam question or something like that. Okay. All right. So let's go ahead and move on into the efficient algorithms. Where are you? There. Okay. Let's see. Okay. All right. So now this is not an algorithms class, but we have talked about this to some degree. Okay, so we're not going to go into great detail about developing efficient algorithms, but just kind of these last couple of classes with efficient algorithms, and then the following week, let's see. I got for the following week, it's where is it? Oh yeah, sorting. Okay, so it's kind of a reclam, kind of like a preview of your future semesters. okay, some future courses. All right. So the idea is to have an understanding of an idea of what execution time might be. Now, one of the things we looked at earlier in this lecture was how we did this whole time thing, right? Where we said, okay, the start time is this, we're going to do some stuff, and the end time was this, and let's see what the difference between those two is, and that's how many milliseconds it ran in. Which is nice, I mean, for us to be able to do that on something that only takes a few seconds. But what we would like to know is how fast would something like this run in, without having to run it and test it every time. So, for example, if I go back to this one over here, the performance thing here. So that end stuff was, let me clear out all these breakpoints. Yeah, there we go. Okay. So we're going to run this. We're going to run this and see how long it takes. All right. All right. And again, the hash set was very fast, the other array list and all that stuff. And we would expect that if we take off a 0 here, so instead of 50,000, now it's going to be 5,000, we would expect that it would take less time, right? So if we run this now, right, so everything takes a lot less time. Now, you'll notice it wasn't a direct, it was a tenth of the size, but it wasn't all a tenth of the time, right? This 14 and 17 is now 3 and 3, which is about a fifth of the size, a fifth of the time. This 4 seconds here and 1.3 seconds here. Okay, so that's about a tenth, a little bit, but this was more than a tenth, less than a tenth. Wow, less than a tenth, huh? This was less than a tenth less. What is it, 64 and 29? Well, that's about a tenth and pretty close to, no, not a tenth, that's a hundredth, right? So we reduced the size by a tenth, by a factor of 10, but the time it took was reduced by a factor of 100, right? Well, that doesn't seem like it makes a lot of sense, does it? How could that be? We reduced the size by 10, by a factor of 10, but the time didn't reduce by a size of 10. Okay. So what we're going to do today is we're going to talk a little bit about why it is that it's not just always a straight reduced by, like, if a problem size is 10 times another problem size, that automatically it's going to take 10 times the amount of time. Okay, that's not how it works in programming a lot of times. Okay, so the idea is we're going to have an idea based on the way that the algorithm, that we can take an algorithm, we can analyze it, and we can discover what its general idea is, what its general runtime is going to be. It won't be an exact number of milliseconds. Okay, it won't always be an exact number of milliseconds. It is the idea that as a problem gets bigger, right, how much longer will a specific solution take? Okay. All right. So first, okay, the execution time of a particular program is going to be dependent on other factors going on in the system. Okay. The second is the execution time could be dependent on specific input, linear search and binary search. All right. If an element happens to be the first in the list, linear search is very fast, right? If we said we want the first, we want to find item X, whatever X is, the value X. And if it happens to be first in the list, linear search is going to be fast, even faster than binary search. Right? So this is what's called, what we'll refer to as the best case scenario. Okay, the best case time complexity. It means the fastest this algorithm could possibly run in. Binary search also happens to be very fast if the item that we're looking for is directly in the middle of the list. Okay. Hopefully you guys remember what binary search was from last semester. Okay. So what we're considering though is what we want to be able to represent our algorithm complexity in is what's called the growth rate. That as the size of the problem gets bigger, how much longer, how much more tasks are needed to solve it. Okay, and I don't mean how many tasks in terms of how many lines of code we're writing, not that. I'm saying how much more does the code itself have to run? How many cycles, how many clock cycles, how many instructions are going to have to be executed? Okay, so what we're going to do is we're going to approximate the effect on the change of the size of the input. So we're going to approximate how much changing the size of the input affects the time of the algorithm execution, of how long it takes for the program to run. Okay. All right. Some terms you'll want to know, this concept of big O notation. So the idea of the big O notation is kind of, it's not the worst case, it's not the best case, although what we would want to know about is the best case, but it's kind of if the best, worst, and average cases all are in the same magnitude. Not the best is usually big O of 1. If the worst and average cases are in the same kind of amount of time to run on a specific input, right, then we can say that that is what its algorithm complexity is. Okay. So let's look at a simple example, the linear search algorithm. We would call that big O of n. Now the reason why we would call that big O of n is because for an array or a list of size n, to find a value in that array, we have to search through potentially every value in the array. Because what if the value is not in our list? Then we have to search through every value, right? And we have to discover that it's not there. So what that means is that if we were to search through the entire array, we would have to search through n elements. Now what we're going to discover is that big O of n, big O of 2n, these are all going to be considered the same. Okay. What we're really after is after a very approximate big O notation. We're not after, what we're not trying to figure out is an exact runtime of an algorithm. What we're trying to figure out is a way to approximate that as a problem gets bigger, as a problem set gets bigger, how much additional time should I expect that the from start to finish that the execution of an algorithm will take. Okay. You may have heard the term order of magnitude before, okay, like the order of magnitude of 100, or the amount of debt that a country has, maybe in the order of magnitude of billions, that kind of idea. It's how much, right? A general notation for how much something is. Okay. Okay. All right. Again, I said that we were talking about the best, worst, and average cases. Best case oftentimes will be big O of, we'll call that 1, meaning we find it immediately and we're done. Right? An average case analysis is really what we're probably after in most situations. A worst case analysis can be useful, right? But we know that the algorithm will never be slower than whatever the worst case is. So for linear search, for example, we might have to search every value in the array, and that would be a worst case situation. Right? What we would probably want would be an average case analysis, right? But we cannot always know what all the relative probabilities of the various inputs and all that stuff are going to be. So what we're probably going to do most often is try to just do a worst case analysis and say that this is the worst possible runtime, the worst possible complexity that this algorithm could be. Okay. Now, when we get to this big O notation, some things that we're going to say, some things that we're going to do, is we're going to ignore what's called multiplicative constants. So if we say, if we do a big calculation and we find out that it's big O of n over 2, well, that's really 1/2 times n. So for big O notation, we just drop the 1/2 part. And what we end up with is big O of n. Why? Because the n is what's the dominating factor. It's, in fact, big O of n, we refer to that as a linear algorithm, as an algorithm with a linear time complexity. What that means is that if f of n equals n, it's a line, right? It's a line with a slope, right? Guess what? F of n equals n over 2. It's also a line. Right? Oh, I need to go this way with it. It's also a line. F of 100n. It's a steeper line, but it's still a line. Right? So we call this a linear time algorithm. And notice that here, if we divide, the input size is 200 or 100. If we divide whatever the runtime is, right, f of 200 divided by f of 100, notice it stays the same, right? It's 200 divided by 100. This is how you can know that it's a linear time algorithm. So the main thing that influences it is that as the problem size grows, the time required to complete the algorithm grows in the same rate. That's what a linear graph does. Okay. We will also do what's called ignoring non-dominating terms. So if we're trying to find the maximum number in an array, if n is 2, it takes one comparison, we're done. If n is 3, it takes two comparisons to find, right? We have to compare the first two elements, find what the max is there, compare that to the third element. If the max, find out which one is max there, and we're done. Right? So you notice that whatever the size of the array is, the size of the list is n, right? It's going to take n minus 1 comparisons. So we could call this big O of n minus 1, but because of what we're trying to do with this very simplified big O notation, we get rid of the minus 1. Right? So now instead of big O of n minus 1, we would also call this big O of n. It's the same thinking if you think about it. If f of n equals n minus 1, that's also a line, right? Okay. And so the main thing is it a line, and is it? We're going to look at some others as well. Okay. Some useful summations that hopefully you've learned at some point. Right? If we sum the numbers 1 up to n, we can replace that with this nifty formula here. Some constant to a power plus a to the next power and so forth. We could replace that with this, and same thing. And so 2 is just replacing a with 2. Okay, which 2 minus 1 is 1. And so this would just be 2 to the n plus 1 minus 1. Okay. So let's talk a little bit about how we can determine the big O notation of something. All right. Some different examples, one involving a repetition, one involving sequence, selection, and a logarithmic thing. We'll talk a little bit about that one. We may not get to the logarithm one, it kind of may take some time. Okay, so we have a repetition of simple loops, of a simple loop. So here in this, we are going to go through I equals 1 up to n, right? And each time through the loop, we're going to set k equal to k plus 5. What this code does doesn't matter so much, because what we're really interested in is, can we look at this code and understand what, right? What is going to, how much time this is going to take based on the size of n, our loop, our loop iterator. Okay. So we would consider that this is done in constant time, some constant amount of time to take k, add 5 to it, and assign it. Okay, we don't really care too much about what that constant time is, and we assume that each time through the loop it'll take about the same amount of constant time. Okay, yeah. Milliseconds type thing. Okay, we're going to execute this loop n times. Okay. Now, if we were really trying to analyze this, well, let me just show you this first and I'll tell you about it. Okay. So our time complexity, some constant c, which is the constant time for this, done n times big O of n. Okay. Again, we ignore that multiplicative constant. Okay. Now, if we were really wanting to kind of analyze this in a more detailed way, let me see if I can do this. Pen, yeah. Okay. Let's call each step, each thing that happens, some different c values. Instead of just c, we'll have c1, c2, c3, and c4. Okay. So what's our time complexity for n, for the size of n? Well, how many times is C1 going to happen? So let's make a little table here. We'll call it the constant, and we'll call it the number of times. Right. So C1, C2, C3, and C4. Okay. All right. So how many times is C1 going to happen? Okay, good, guys. 1, yeah. Okay, so C1 is going to happen 1 time. Let's get back to C2 and C3 in just a moment. How many times is C4 going to happen? All right, because we already talked about that. This happens n times. Okay. Now some tricky ones. How many times is C2 going to happen? Yeah, See, C2 represents the testing of if this is true or not. It's not an assignment, right? It's the testing. Well, let me ask you something. If n were 0, this would still get tested one time, wouldn't it? If n were 1, this would get tested the first time through the loop. It would execute. Then it would come back, and 2 is less than or equal to 1 would not be true anymore, so it would be tested twice, right? So those of you who are saying n plus 1, yeah, we're going to test it always one time at least, and then we're going to test it every time through the loop from then on. So C2 is actually n plus 1. Okay. C3. How many times will that one happen? How many times will we increment I? You guys say n minus 1 and plus 1. Okay. Let's say that n was 1. Okay. If n was 1, okay. If n was 1, I equals 1, I is less than or equal to 1, we do this, we do 1 plus plus is 2. Is 2 less than or equal to 1? No, 2 is not less than or equal to 1. So therefore we did this one time. If n was 2, right, I is equal to 1, plus plus, I is equal to 2, true, so we do this, then plus plus, I is equal to 3, 3 is not less than or equal to 2, so we're done. And we did this twice. So you see the trend here? Okay. That C3 is going to be done n times. Okay. All right, so this will become, if we really want to be able to have a slightly more detailed analysis, we would end up with this. So our T sub n would be C1 plus C2 plus, and I'm doing a bit of quick math here, C2 plus C3 plus C4, all that times n. Okay. So if we talk about ignoring non-dominating terms, so this is a non-dominating term because as n grows, this doesn't change. This is a non-dominating term, so as n grows, this doesn't change. And then this basically, this whole thing here is basically what this is right here. Okay. So those are the same thing. So we still ended up with a C times n, big O of n. Okay. So a slightly more detailed way of showing it. Okay. All right. All right. All right. So what about nested loops? And we're just going to stick with the no, not late. Oh, okay. Actually, okay. So here, just like in before, this code is going to result in a constant time. Our inner loop will be executed n times. Our outer loop will execute n times also, right? So what is our time complexity? Is it n plus n? Is it? Yeah. You guys must have been through this before. You've been looking ahead, right? It's n squared because it's n times inner loop executed n other times. So if this were 3, for example, this would be executed 3 times. This would execute that same loop 3 times. So it would be 3 times 3, which would be 9, right? And so forth. So we're looking at an n squared algorithm. So as n grows, our time complexity grows by n squared. This is why this has to do with why in the example I just showed you a few moments ago, the in the Java code, the set list performance, why when I decreased the problem size by a factor of 10, it did not decrease the runtime by only a factor of 10. It decreased it by sometimes, in some of those cases, by a factor of around 100, right? So here, look, if I had a problem of size 10, if n was size 10, then this would execute 100 times, right? This line would execute 100 times, 10 times 10. Now, if my n becomes, instead of 10, but 100, now this same line, instead of executing 1,000 times, 100 times 10, it would execute 100 times 100, which would be 10,000 times. Okay? That's what an n squared algorithm does. The time complexity means that as the problem grows, as the problem gets much bigger, the time in order to solve that becomes that much bigger. And it works the other way as well. As it becomes smaller by a certain factor, the time to becomes that much shorter by an n squared factor. Okay? All right. Okay. All right. Now, what about this one? This one's a little bit more difficult, isn't it? Okay. Now, we made one simple little change. Instead of looping through from 1 to n, we're now looping in from 1 to I. What do you think? And why do you think? What is it? Some things that we know for sure right off the bat. Constant time, right? That line is going to be executed in constant time. We know that. Yeah. Okay, Recep, you're thinking right. I think you're thinking right, because here's the thing: is the inner loop gets executed I times. Well, what is I? The problem is that I isn't the same every time through, is it? The first time through the loop, I is 1, so it executes 1 time. The second time through the loop, I is 2. Right? The third time through the loop, I is 3. The fourth time through the loop, I is 4, and so forth. So what we end up with, we execute that n times, is something like this, where it's constant time plus the second time through the loop, 2 times the constant, plus 3c plus 4c plus 4, and so forth, all the way up. All right. All the way up to the last time through the loop, I is n, and we execute this n times. So, do you remember back? Let's go back to slide. What slide number was it? Okay. That looks a lot like this, doesn't it? Constant times 1 plus 2 plus 3 plus 4 plus 5 and so forth up to this. So constant plus 2 constant plus 3 constant and so forth. We'll replace that with this constant times n plus 1 over 2. Okay, which if we multiply it out, what we end up with is a constant over 2 times n squared plus a constant over 2 times n. When we apply that whole, ignore the non-dominating terms. So we get rid of this because it's a non-dominating term. N squared grows a lot faster than n, right? N squared goes a lot faster than n, so we can get rid of this one. And then when we ignore the multiplicative constant, the constant that's multiplied by n squared, we're left with just big O of n squared. Right. Now, I want to make sure to point something out here. Just because this is big O of n squared, and this is big O of n squared, does not mean, and I'm sure you understand this, does not mean that these two algorithms would take the same amount of time, right? This algorithm would always take n squared times whatever this constant time stuff is, right? This algorithm would by necessity take less time because the first time through the loop it would only go through this one time only. The second time it would only go through this 2 times only. So this would take less time. Okay. We're not after an exact amount of time that the algorithm is going to take because we can only really figure that out by writing the code, running the code, and checking how long it takes. Okay. And we don't really want to do that. We don't want to have to do that every time before we start writing code, right? What this is about is not about finding out which algorithm specifically absolutely is going to take less time or more time than some other algorithm. It's more of an idea of as the problem size grows, how much more time will the solution take? How much more time will the execution take? Okay, in general. All right. So even though they have the same big O, we can also look at this and say, okay, but I know that those two will not absolutely take the same amount of time, right? Okay. All right. So bit of a tricky question, bit of a tricky one here. This one. Another nested loop. What do you guys think about this one? Okay, interesting thought. Well, let's go through some things that we know. Let's kind of analyze it, things that we know. We know this is going to be constant time. The inner loop is going to be executed 20 times. Not based on n. So the number, so how long this inner loop takes n doesn't matter. The size of n doesn't matter. All right. But the outer loop is going to be executed n times. So this inner loop becomes a constant value, as some of you are pointing out, 20 times c. Okay. So basically it becomes 20 times c times n. Well, guess what? That's just a multiplicative constant, as is this. We can get rid of those and big O of n. It becomes a linear algorithm. Okay. And that makes sense because what this says is that if n grows by a factor of 10, the execution of this should grow by about a factor of 10 as well. If we multiply n by 100, the amount of time that it takes should multiply by about 100 as well. Okay. All right, a couple more. Okay. Sequence. This followed by this. So you've learned how to do the loop. Okay. Take a look. So, yep, so this will be executed 10 times. So this becomes a constant. This portion of the algorithm is a constant. All right. This becomes just like the same previous problem. So 20 times n, so executed n times. So what we end up with, someone wrote it, Recep, you did, right? So this first portion becomes c times 10. The second portion becomes 20 times c times n. We can get rid of the c times 10 because it's a non-dominating term. We can get rid of the multiplicative constants. Right? So when you have a sequence of some set of code followed by another set of code, we add them together. So when it's inside of a loop, we multiply it. When it's sequential like this, we add it together. Ooh. Selection, if statement. This could be a difficult one, right? Because this and this don't have the same execution time. But we don't know what we're going to do here. Okay. By the way, they're giving us a hint on this that this list contains test happens big O of n times. So let's say the list, when we say n, we mean the number of items in the list. Okay. All right. Let's take a quick look. All right. So if we let n be the list size, so this for loop will execute n times. Okay. So the way that we do this is we will have the test time, whatever that is, plus the worst case of the two. So notice that if this is true, if it contains E, what happens? We just print out E. Right? A print line statement like this is a big O of 1, what's called a big O of 1, meaning it's constant time. We'll get into constant time in the next slide. Okay, so this is considered constant time, and this is considered big O of n times because we're going to go through the entire list, printing out every item in the list. So what we do is we say, which of these two is worse? Big O of 1, constant, or big O of n? And the one that's worse is the big O of n. So we say, okay, this is going to be the one that we assume in the worst case scenario, we go there. Okay, so it's going to be big O of n plus the amount of time that it took to test the if statement. In this particular situation, it was also big O of n that we searched the list to see if E was in the list. So what we end up with is a big O of n plus a big O of n, which means n, big O of n. Okay. The reason why this plus this equals the same thing again, I know 1 plus 1 equals 1. How is that possible? But remember, we're dropping off those multiplicative constants. We're not after an exact, 2n plus 23, n squared. We're not after that. What we're after is what is the dominating factor that decides how long this algorithm is going to take to run. Okay. All right. So big O of n plus big O of n is still big O of n. Okay. And like I said, we would get into constant time, but it's break time. So here's what we're going to do is we'll take a break here and then come back at 3:30 and continue on today. Okay. All right. I'll see you guys in 10 minutes.